Well, to understand multi-phase flow separation, the first thing you've really got to understand is what multi-phase flow is. In thermodynamics, when we talk about a phase, we're talking about a distinct region of the system where the fluid properties are homogeneous. Typically, that means when we're talking about a phase in terms of oil and gas or flow, we're talking about a distinct fluid or state of matter. So, for example, we might be talking about gas, oil, and water. In addition to which, we talk about individual liquids sometimes as distinct phases. For example, oil and water, just because they have a property known as immiscibility, which means they don't mix. When we work in an oil and gas field, what we do is we bring up the fluid we want, for example, oil or gas. But typically, it's not pure. There's a mixture of contaminants in there. For example, other types of gas or water with the oil, or even a combination of all three, and sometimes there's solids in there as well. And therefore, in order to handle the fluid, the oil or the gas, what we want to do is separate out the contaminants that weren't meant to be there. And we use devices called multiphase flow separators to do this. The problem with multi-phase flow meters is that although the technology has been around for some time, we're still not at the point quite yet where we can make very accurate predictions of individual phases within a multi-phase flow stream. Therefore, there's still ongoing research, and NEL is currently in the process of developing a number of facilities to test and calibrate and perform research on this type of flow metering technology. The main challenges associated with handling multiphase flow from our standpoint are the measurement issues associated with trying to measure a liquid stream or a multiphase flow stream which has multiple phases. For example, trying to measure oil, water, gas, solid together in one stream makes it very difficult to characterize exactly how much of each phase or even what the overall flow rate is in that stream. In order to get by this, we're looking more at multi-phase flow metering technologies. Traditionally, the approach is to use multi-phase flow separators, and what they do is they use test separators, for example, in an oil and gas field, and they'll sample the multi-phase flow, and then they'll break it into its constituent components and measure using single-phase flow meters. However, the cost and the infrastructure required to do this, often in hugely remote parts of the world, is extremely expensive, extremely time-consuming, requires a lot of effort. So it's much more convenient if it can be done with a single flow meter that measures all the individual phases. Multiphase flow separators essentially separate multiphase flow into its individual phases. On an oil and gas platform, for example, this means taking the oil, water and gas, and even the solid particles, perhaps sand or whatever else is produced from the oil and gas well, and separating into the constituent components. There's a number of reasons you'd want to do this. However, the two, when we're talking about the oil and gas industry, the two primary reasons are for production and well testing. Production separators essentially just separates bulk fluids into their individual components and ship them to a terminal where they can be processed. Test separators basically sample the well, so you take a smaller sample and you can test the quality, and you can use single phase flow meters to establish what the individual flow rates of each phase are that you're producing from the well. A huge range of different technologies which are used to separate different types of fluid from one another. However, the most common type of separator that you see across the world is the simple gravity separator, and that's essentially a large pressure vessel where commingled fluids are passed into, and given that the fluids tend to have different densities, it just uses gravity, and essentially one fluid begins to float on the other fluid, and then you can siphon one off or drain one out and separate them that way. However, when you have a large separator vessel like this, it's ideal if you can improve the efficiency a little bit by using one or more additional separation technologies. One of the technologies which is quite commonly used is a momentum type device. So on the inlet, for example, you pass the fluid through, and it's passed through a vein which very quickly throws the commingled fluid around a sharp radius and enhances the gravity effect. So the centripetal acceleration causes the heavier phase to be thrown outward to a larger degree, and it causes faster separation. So by the time they actually reach the body of the vessel, they've already been separated to some extent. Other types of separators which you see for more specific applications, for example, trying to separate out entrained gas particles or liquid particles from a fluid, are sort of coalescing type devices, mesh pads, coalescing plates, this sort of thing. And they take advantage of the fluid properties, the surface tension of the fluid. And when the fluid hits the plate, they coalesce into larger particles which separate out faster. They settle much faster. So it's a combined effect of a number of different separator technologies. For a multi-phase flow separator, in an ideal world, the outlet streams are single phase. So for example, for a three-phase flow separator where you have oil, water and gas, the outlets would be oil, water and gas without any contamination. In these instances, you use a simple single-phase flow technology, a turbine or a Coriolis type flow meter, which are very well established and are very accurate for single-phase flow applications. In some instances, the fluid which we get from the outlet is contaminated to the extent that measuring it is substantially more difficult. What we do in these instances is we use a second stage separator to further clean the fluid stream, and then use a single phase flow metering technology. The other case we have is where we're using a two-phase separator for a three-phase flow. So for example, the two-phase separator would separate out liquid and gas, and then we'd take the liquid stream, which might be a mixture of oil and water, and use a water cup meter to figure out exactly what the constituent components and what the sort of volumetric flow ratio is in that outlet stream, and therefore we can use a two-phase separator to establish a three-phase flow. The typical problems you see with separator design, in terms of flow measurement anyway, are undersized separators. That's possibly one of the most common, where a separator isn't quite big enough for the amount of flow which you're attempting to separate. The problem there is that separators, when you pass a liquid into them, the size of the separate dictates how much retention time you have for a given flow rate. If the retention time isn't great enough, the quality of the separation won't be particularly good, and you're likely to get fairly heavy contamination. Other problems might be associated with if you have solids, maybe sand, entrained in the flow, then it might be damaging for equipment. It may not be separated out. It may damage flow meters and other process equipment downstream. So in which case it would be important to include some sort of separation device to try and separate out any solids, any sand particles or anything like that, which might be entrained in the flow. Depending on the process, foam emulsions may start to form. Emulsions are when two liquids, like oil and water for example, which are immiscible, are subject to heavy shear, and due to this they form a sort of sludgy mixture which is extremely difficult to separate, and sometimes it's almost impossible to separate them. There are demulsifiers and other chemicals which can be used. However, for our test facilities here at NEL, we don't tend to use these because we're very tightly control the fluid properties in the test line, so this can be a big problem for us depending on the test. However, typically we monitor this very closely in order to ensure that contamination is kept to a minimum. The other problem you tend to see quite frequently as well is if you have a high viscosity oil, for example, the size of particles can be a significant issue. So if a fluid like an oil and is flowing with a gas, like natural gas for example, in an oil gas application, and is passed through a pump or subject to heavy shear, the particle sizes of the gas which are entrained in the liquid can be very small. The problem is with high viscosity liquids that they won't separate out very easily, and you'll end up with these micro bubbles trapped permanently in the liquid.